Derived. Snails and students. Alright, one day when suddenly a Dalek walks into my classroom.
So there's this hunter, and he wants to shoot a monkey for some reason. Welcome back. This time we're going to have a look at some astrophysics and cosmology. Astrophysics is what stuff is out there, and cosmology is to do with how it all got there. We're going to have a look at how understanding the Doppler effect allows us to analyze the light from stars in more detail and learn quite a few different things about them. Let's first recap on what exactly the Doppler effect is. This equation describes it, and it says the frequency you observe depends upon the frequency of the source of your waves, as well as the speed of those waves, and finally how fast that source is moving. For a stationary source, this term is 0, and this term cancels out, and you see the frequency remains the same. But if your source is moving, things are a little bit different. You see, for a stationary source, waves travel out in circles or spheres in all directions, and the circles are concentric. That means they have the same center point. But if your source is moving, then each circle has a slightly different center as it travels through space. This has an interesting effect. In front of the moving source, the waves appear to be compressed. That means they have a smaller wavelength and a greater frequency. Behind the moving object, you get the opposite. If there was an observer at the back of the car here, they would notice a lower frequency and a higher wavelength. So this is not just an interesting phenomena though, we can make very practical use of this. For example, this is a police radar machine. Instead of just looking at the car and maybe trying to do this based on the sound it's given out or the light that's coming off of it, we actually shine a radio wave onto the car. The reflection of that radio wave then acts as a very strong source. This allows us to get a precise measurement. So a radio wave gets sent to the car, it gets reflected back, and the receiver looks to see how the frequency has changed. The greater the speed of the car, the greater the Doppler shift. And if the speed is too high for the particular setting, the rest of the equipment takes a photograph of the license plate, and that allows the police to send a speeding ticket to whoever's breaking the rules. We can also use these things to try and work out the speed of maybe a tennis serve or a baseball pitch. It's generally quite a nice way of doing it whenever you can't physically interfere with the action. So for sports, for example, you don't want to be trying to recalibrate your shots in the middle of a game. Now you might say, well, for stars, surely this should be just as easy. If we look at a star that's traveling away from us, the frequency will go down and the wavelength will go up, and the light might appear to be redder. And if the star comes towards us, it would appear bluer. It turns out that is true, but one confusing point might be that if you look at the night sky, you can actually notice that some stars are red, some are blue, and some are in between, which gives them a white appearance. And some people mistakenly believe that that's all to do with the Doppler shift. The Doppler shift is an effect, and you do notice it, but it is incredibly minor within our own galaxy, and it's not nearly a big enough effect to actually change the whole color of a star. To give you a word example using this equation, I'd like to start with a rather bad joke. So the idea is Bob's driving in his car and he's not paying much attention. So he comes to a junction and the traffic light is red, but instead of stopping, he misses it and he goes straight through. There's a police officer watching and she notices the light was red, and of course she pulls over Bob and starts writing him a ticket for failing to stop. But Bob's a bit of a cheeky chap, and he was paying attention at higher physics, and he thinks he's got a way out of this. He says to the officer, look, you can't give me a ticket, it's really not fair, you have to blame the laws of physics. You see, I was travelling towards that light, and therefore the frequency was blue shifted, and that means the red light appeared to be green for me. So I did nothing wrong, and you can't give me the ticket. So the police officer, well, she doesn't really buy it, but she plays along and says, are you sure, Bob? I mean, if you're willing to write that down as a statement, I'll accept that. And that's what he does. So he writes a little statement and he signs her book saying that's exactly what happened. But sadly, it doesn't work out for poor Bob. Instead of getting off with a ticket for failing to stop, instead she has to arrest him and impound the car, and he actually ends up going to jail for incredibly dangerous driving. You see, the police officer was also paying attention in higher physics, but instead of just being able to describe the pattern, she was able to do it with actual numbers. And when she heard Bob's story, she did a quick sum in her head, and she realised there was a problem. Because if he really was travelling fast enough to blue shift the red light all the way down to green, then that's a very, very serious problem indeed. Because it turns out you need to go about 100 million miles per hour to do that. So poor Bob's off to jail and he's got no chance at all. Bad jokes aside, let's actually have a look at the numbers involved in this, because this particular equation can sometimes tangle up people a little bit. So the first line just states the equation, and then for the second one, what I've done is I've went to a reference source, you'll have one in your data booklet, and I've pulled out values for the frequency that Bob claimed, which was green. So 560 is in the middle of the green range, and red was in the middle of the red range here. You might have to do that sometimes in an open-ended question, or perhaps you just have to look something up in particular. You do know quite a bit about the visible spectrum. Secondly, we know the speed of the wave. It was the speed of light, 3 times 10 to the 8. And the thing we're trying to find is the speed of the source. It's a takeaway in this equation as opposed to the plus, because we're blue shifted, where the source is coming towards the light. So the first line, we get our mark for the equation, we get our mark for all the substitution, that's great. And then quite a few people tend to go a bit wrong here. You see there's 1, 2, 3, 4, 5 different terms, and the algebra is a bit trickier than usual if you try and rearrange from there. The best bet, I would say, is to actually deal with as many numbers as possible. One way would be to divide this over here and then turn that into a fraction, but what I've went with in this case, I've said this is a number and it's multiplied by that number, so my calculator can simplify this for me. I get one number instead of 2, and that means less algebra, which is where people tend to go wrong. For the next step, I've taken the whole denominator here and multiplied both sides by that, so it effectively moves up here. And then I've divided both sides by the 560, so it moved down. When I'm at this stage, I have two numbers again, and any time there's two numbers, it's always a good idea, get the calculator out, turn it into a simpler number. One number is always simpler than two. And at this stage, well, I add this to both sides, and then I take this from both sides, turn it all around, and we have this sum here. Taking the difference gets us this value, and that's roughly 10% of the speed of light, or a bit more, maybe 20%. And then to convert from meters per second into miles per hour, you don't need to know this factor, but it's about 2.2. You need to multiply by. Now, more generally, if we want to look at stars, we need to figure out what we can do. We said before that although redshift and blue shift does happen with them, it's a relatively subtle point. So you can't just look at the entire colour of the star and try and measure that, because it's far too tricky. Instead, we need to think back to National 5 a little bit. So at National 5 we said any dense material that's heated up will emit a whole spectrum of light, and it will be continuous. In the case of a star, that spectrum often includes the visible spectrum, so you get every single colour of the rainbow being produced by your star. The problem is for that is the outer parts of the star are a bit cooler. So the core where the light is made is right in the centre, it's very hot, they give out all the colours of the light, but the outer parts actually block some. And you end up with something that looks like this. There is an absorption line spectrum. You can actually quite easily see this if you go outside with a handheld spectrometer that's reasonably inexpensive, point it at the sun, and you'll see just that. You have to look quite carefully because the lines are very thin though. Now, to be entirely fair, if you're viewing this from outside, you're actually looking through quite a lot of miles of air. So those lines could have been absorbed by our atmosphere or a cloud or a tree if it was overhead, that kind of thing. But even when we do these experiments from space or in hot air balloons that are very, very high up, we still see the same effect. This was actually used to find the existence of helium. Helium is named after the sun because at the time we thought that was the only place we could find it. It was this unknown special element. Turns out there's quite a bit around Earth, but because both hydrogen and helium are very light, they tend to float higher and higher and higher and get blown off into space. So there isn't that much of it around. Every single element has its own individual fingerprint. If you have it in a lab and you heat it up, it will give out light at certain colors. Those colors are the same as the colors that it would absorb if you tried to pass light through it. So rather than trying to look at the color of the whole star, we have a look at its line spectra. If that star is moving away from us, all of those lines move slightly towards the right. This way we can also figure out what the sort of chemical was. For example, here we have two green lines very close together and then another one a little bit apart. That's quite a clear signature, and if we see that pattern but slightly towards the redder side, that tells us we're still looking at the same chemical, it's just coming from an object that's moving. Now you might say, why do we care so much about how the stars move? Well, it turns out this is actually one of the few things you can do in astronomy. There's so much out in the universe and there's so little we can do with it. You can't grow your own pet star, you can't try and visit them and take samples. The only thing we can really do is just look at them. So it's actually really quite fortunate that we have this effect, because this turns out to be the key to unlock pretty much everything we know about them. In astrophysics, we don't usually use the Doppler equation as it was originally made. We tend to prefer to talk about wavelengths, and we also talk about a certain fraction called Z. And it looks a little bit like this. To get the new equation, we need to start with the Doppler one, here it is, and then what we do is we replace a bunch of the names. So instead of talking about the speed of the wave, we're just going to write C for the speed of light. F source, I'm going to call F rest, and F observed will just be FO. Speed is just speed. We can then swap from frequency into wavelength with the usual wave speed equation. V is F lambda, so F is equal to V over lambda. We swap one of them here and the other one there. It's the same idea. Next, because I want the wavelengths to be at the top of the equation, I'm going to invert both sides. That means do 1 divided by that side. And it ends up looking something like this. We now have a common term, the speed of light's on both sides, so we can divide through by that, and that simplifies things further. For the next step, what we need to do is multiply both sides by C, so it goes over here, and then apply the common factor to both terms inside the brackets. So we end up here. Next, our goal is to find a way to unite all the values for C. So I'm going to take this term and I'm going to subtract it from both sides to end up with a new line. Next, we have a common factor of C. We can take that out of the bracket, and then we end up with something that starts to look like the final version. The last few steps are to swap things around a bit with some algebra, and then this term V over C we're going to give a special name. We're going to define this letter Z to be the redshift factor, as it were, and we're going to call that the speed fraction. So we can swap that in here, and that completes our new equation. There is a sort of fuller version of this. It's not actually part of the higher course. The ones you receive in your equation sheet are these ones in red. But it can be helpful to talk about these things because you could come across them online. It's basically saying this Z fraction is the ratio of speeds, or the ratio of change in wavelength over rest wavelength, or change in frequency over rest frequency. It's kind of similar to Snell's law in that respect. So how about a worked example? Well, here's one. Light from a distant galaxy contains spectral lines of hydrogen. They had a look, the pattern looks like hydrogen. But when they measured one of the lines, one of the ones they were particularly interested in, it has a wavelength of 466 nanometers. Now, normally when they're on Earth and they measure that very same line, it's only 434. So this tells us something. It tells us that the wavelength has gotten smaller. Sorry, it's gotten bigger. The bigger one is the one we measured out in space. This means that this thing has been redshifted. This galaxy is travelling far away from us. And that's what we're going to try and work out. So we've already kind of answered part C. And then anytime you're asked anything at all about this Z, there are only two equations that include it. And chances are, if you have a multi-part question, one part will use each of them. So as soon as you read almost anything about galaxies, chances are it's a question using these equations. For the first part, what we're going to do is use the first one here. We know something about wavelengths and we're asked to find Z, so that's hopefully straightforward. We put the numbers in. You have to be a little bit careful to know which one you're going to do twice. Is it the big one? Is it the small one? It just depends. The reference value, the stationary value on Earth, is always the one on the bottom. Okay, that's always going to be the case. You have to be careful there. And the reason that's the rest one is because when we're in the lab, the sample isn't moving compared to us. You might say, well, why have I not bothered to write in the nanometers? This whole term is nano, nano, and then it's divided by nano. There's a common factor of nano up and down above the line. So that means it's going to end up cancelling out. And I'm just making it a bit simpler. If you want to put those in, it's perfectly fine. It will cancel out anyway. This is a mistake because it's the same mistake again, the same step again. And if you do this sum on your calculator, you'll end up with this value here, 0.07. How to interpret that? Well, you're going 0.07 of the speed of light. That's kind of the idea. Our final step is to round, and then normally we would put units in. But Z is unitless because it's a ratio. Little point on rounding. People often find this quite tricky, but it's actually a really simple rule. We have loads of numbers here. Most of them are nonsense. They're made up. Basically, the calculator's telling lies because we only know the first three numbers in our data. So we have three useful numbers, or three significant figures as we formally call it, which means my final answer should have three useful digits. The zeros at the start don't count, and a bunch of zeros over here won't count either. It's three numbers that mean something. So that's how I'm going to round that. For part B, we're asked to find the speed at which the galaxy is moving relative to Earth. So we're going to use the other equation. Sometimes people get a bit confused and they might use, say, v equals f lambda. They know that from National 5. They have a wavelength and they want a speed, so they kind of really want a frequency somewhere. So they just find any old number and pretend that's the frequency. Doesn't tend to work out for them. So we know z, we're going to take that over and we're going to put it into this equation. That leaves just the unknown of v, and if you process through the working, you'll find it's this number here. And part C, it was moving away from us. Because we're not asked for an explanation, we don't need to provide one. Another point that was part of National 5 but is often missed out is that we know a little something about the colour of stars too. You see, there's a sort of temperature scale. Anytime you have a solid or a dense fluid like in the star, the colour that they glow actually tells you something about their temperature. See, here is a picture of a blacksmith that needs to control the temperature of the metal they're working quite carefully. If you heat it up too much or too little, the properties are very different. So when the metal's hotter, you can shape it better, but they also need to control the temperature so that it becomes nice and strong when you end up with the final product. This temperature scale is a blacksmith's colour chart, and it works quite nicely. You can even say that the temperature red hot, for example, is an actual temperature. Many people think it's just an expression. But the same thing applies for stars. This chart here allows you to map the appearance of a star to its temperature. And there's actually an equation for this which is well beyond the higher course and possibly beyond the advanced higher course. This equation describes the relationship between the temperature of a star and the distribution of the light that it gives out. So that's quite a mouthful. What do I mean by that? Well, if you have a star that's quite cool, let's say 3000 Kelvin, then it will give out light according to this curve here. Most of the light is in the infrared range, below red, and there's a little bit in the visible. So this object will be glowing a sort of dullish kind of red. Think of a coal on a fire, that kind of thing. If you have a hotter star that's say 1000 degrees hotter, well, because it's hotter, the amount of light it gives out at every single wavelength or frequency will be higher. So it gives out more infrared here, more infrared there, more infrared there, but it gives out a lot more visible. So not only is the green curve above the red one, the peak of it has also moved to the left. See, the peak of the red line is almost 1, the peak of the green line here is about 0.75 micrometers. And if you go for a hotter star again at about 5000 Kelvin, well, your peak is actually in the middle of the spectrum, so that one's going to appear nice and white, and we see that down here on this chart. Now, why is this helpful? Well, it helps us address a very tricky problem. You see, if you want to look at stars, then one of the main things you want to find out is how far away are they and how big are they. That's sort of the basics. But there's a problem. If you compare a small star that's near you to a big star that's further away, they might actually appear to be exactly the same. You can't just look at a thing and figure out how big it is, because it could be any size. Some of them are thousands of times bigger than others, and there's really no way to figure out like the width of a star from the measurements, because they all just appear as little dots. So what are we to do? Well, the trick is to use this peak. You see, our physics knowledge of astronomy tells us that the mass of a star determines its size, and therefore the pressure inside, and therefore the temperature. Once you know the temperature, this equation allows us to work out the maximum or the peak wavelength of light that it gives out. And it's fine, you see. So if you have a star that's further away, well, the light will spread out through space as it approaches you, so you won't see all of the light, but the peak will still be in the same position as the peak. If you take this blue line, for example, and you assume half the light never reaches you, well, the blue line will be half as tall at every single position, but the peak is still going to be where the peak was. So no matter how far away the star is, you can still work out its size and temperature from the peak. If you then plug in the numbers for that peak into this equation, you can work out how much light it gives out. So how much light started leaving that star, and then you compare the light that is received by our telescopes, and by comparing the two, you can work out how far away it must be. So this little trick tells us the size of the star, which includes its mass and its volume, as well as its temperature, and last of all, how far away it is. This also ties in with the next effect. You see, if you have a star of a particular size and therefore a particular temperature, you'll get a line that shows all the colours of light it gives out. So this one here is a bit hotter than our sun because the peak is in the green zone. Right? Fine. If you then take a close look at the light coming from it, you'll notice there are dips. And these dips correspond to the absorption lines of whatever material is made in that star, which is almost always hydrogen. So we know what to expect, and it turns out pretty much everywhere we look, almost everything is hydrogen. So that's nice because it really simplifies the analysis. You're only ever really looking for one set of lines. So the dips correspond to hydrogen, and that allows you to figure out the positions. By comparing that to the reference value, you can work out how fast that star is moving. So now we know its position and we know how fast it's moving. This little chart here shows of all the material in the universe that we've been able to survey 3/4 of it is just plain old boring hydrogen. And the remaining, almost all of the remaining quarter, is helium, and then everything else is this little sliver here. This suggests that either the universe started with a bunch of complicated things and has gradually been broken down into hydrogen, which seems unlikely, or perhaps the whole universe starts off with only hydrogen. Our current understanding is there was a big bang and it cooled down gradually until hydrogen was able to form pretty much everywhere. What we understand has happened is the hydrogen in some places collected under the pressure of gravity and formed new stars. The core inside the star got hotter and hotter and hotter, and eventually fusion reactions were possible. The fusion reaction turned a bunch of the hydrogen that was at the start of the universe into this helium. That is the primary driving force behind all stars. It is what powers the universe. But energy alone from this process wouldn't make a very interesting place to live. It's this little sliver where everything else happens. You see, stars that are like our sun, they can only ever burn hydrogen into helium. And it's not really burning, it's a fusion reaction. Once they start running out of hydrogen in their core, well, they just kind of stop. But bigger stars, they can go further. They can take the helium and more hydrogen and make other elements. They can make bigger ones. And the very, very big stars can go all the way up to iron. So if you look at the remaining chunk here, whatever's in here, if you maybe say dig up samples of what's on Earth, well, you don't notice much hydrogen or helium. It's so small it's all kind of blown away since Earth was formed. But there's a fair bit of iron. And there's a fair bit of other materials that are smaller than iron. But as soon as you go above iron, all those elements are really quite rare. And we have an explanation for that as well. It turns out when you do the maths on fusion reactions, basically combining small elements together to make bigger ones produces loads and loads of energy, but not anymore once you go past iron. Iron is the sort of natural minimum, if you like, in terms of energy. The big elements break down towards iron and release energy. The small ones combine together and go towards iron, also releasing energy. Iron's kind of the place all the atoms would like to be. So you might say, well, where did everything else come from? How do we make all the stuff that's bigger than iron? And it must be a relatively rare event because there's very little of it around. We have an explanation for that one too. The very, very, very big stars, they don't just fizzle out, they actually explode. And we think that's what was responsible for providing all the material to build planets, moons, and ultimately people. Once the very, very big stars have turned all of their core into iron, there's no more fuel for them. And the reaction stops. The outer parts of the star then collapse inwards. And it collapses and collapses, falls, falls, falls. And then when it hits in the middle, there's like a big crash. That shockwave bounces off the core in the middle and then explodes outwards. This is a supernova. One star going supernova can outshine an entire galaxy. They're incredibly energetic events, and they're absolutely spectacular. We don't tend to see many of them though, but we have caught a couple of them. So the idea is the first generation of stars lived in a universe that was pure hydrogen. They gathered up, they started making slightly bigger things. Most of them just kind of fizzled out and died, lying about somewhere. We still can't see them because they're, well, dead. They don't give out any more light. But the really big ones made larger elements and then exploded outwards. And all that energy that was released in that final explosion forced together a bunch of these heavier elements, which then created all of the elements above iron in the periodic table. These elements get thrown out across the universe, and that shock wave squeezes other clouds of hydrogen that so far haven't made stars, and that starts off new solar systems. The idea is the second or third generation of stars have new ingredients. They have ingredients that allow planets to form, and then they have planets that allow life to form. That's the basic story. So not only can we work out the contents of the universe and where much of it has come from, we can also answer other questions too. One of the main questions that gets most people interested in astronomy is the big question: are we alone in the universe? And so far our efforts have been, well, we haven't found an answer really, we haven't found anyone else. But one of the things that we've been very much interested in for quite some time has recently been answered. One of the big questions was, how big is the universe? We'll later on see that, first of all, we thought there was just a bunch of specks of light. And then we realized that all the stars in the sky were basically solar systems. Later on we realized that the galaxy is absolutely huge. There are billions and billions of stars within our galaxy. And Edwin Hubble was the one who discovered that there are many more galaxies out there. But all the stars in the universe doesn't really help the question if there aren't any planets around them. So one of the burning questions for the last, say, 15-20 years has been how many planets are there out in the universe? And roughly speaking, we think planets that are a bit like Earth are likely to support life, and the ones that are very, very different probably won't. And one of the ways we can detect planets is using a method based on line spectra and the Doppler shift. You see, if you have a planet going around the sun, or a star, it's too dark. It doesn't really give out much light, so you can never really see the planet unless it's really, really big, in which case it's not interesting because it's so big it's probably a gas giant and therefore it can't support life. But if you have a planet going around a star, we sometimes make the mistake and think of it as the planet orbiting the star, but really they both orbit each other. They both orbit their shared central point. Now obviously that point is very close to the sun or the star, and in most cases it's actually inside the star itself, and really all that you see is a bit of a wobble. But if you have a very big planet next to quite a small star, it can be quite significant. And if you have two stars together, it's a binary system and it's very clear indeed. But what you get is the motion of the lines sort of sways from side to side in a periodic manner. When the star is moving away, the whole light is redshifted. When the star is moving towards us, it's blue shifted. And when it's going sideways, it's basically neutral. What we can do with that is track a particular wavelength over long periods of time, and then we can map out what looks a lot like a sine wave. The time from one peak to another is the orbital period of that star, or more likely, the planet. I am simplifying a little bit here. Most star systems, it turns out, have multiple planets around them, which is good news because it's very common, but bad news because then it gets a little bit tricky trying to separate out exactly how many planets are there, because they all kind of mess up the overall pattern. There's a little bit of extension knowledge here, but what this is saying is if you have this data, if you know the length of a year in time, using Kepler's third law, which is very old physics, you can work out the distance from the star to the planet. And that helps quite a bit, because if you remember, we already know the size of that star as well as its temperature. So we know how much light it's giving out, and we know how light travels through space. So if we know the planet, or how far away it is, we can work out if it's going to be hot or cold. That allows us to figure out if there's likely to be liquid water, and that in turn allows us to make some judgments on how likely there is to be life there. From this equation, if you know the mass of the star as well as the orbital radius, you can also work out the speed of the star. And then finally from that you can work out the mass of, sorry, not the speed of the star, the speed of the planet. And from that you can work out the mass of the planet. This is advanced star equations based on rotation. But the overall pattern is, from looking at this swaying side to side and the other information I've already told you, we can identify if there are planets, how big they are, how far they are from the star, and how much heat they're going to receive on an annual basis. This allows us to work out if the planet's too big, it will be a gas giant, so no use. Too small, it will have no atmosphere, so no use. If it's just in the right range, the Goldilocks sort of zone of both size and temperature, we think that's a good candidate for finding life. This process, as well as other methods, have worked together recently, and we have discovered that there are many, many planets. Most stars in our galaxy that we've surveyed have planets, and there are quite a number of them that are close to being like the Earth. So we think our galaxy is kind of chock-a-block. There are hundreds of billions of stars, most of them have planets, a portion of them will have Earth-like planets, so if life is if it's anything less than extremely rare, there's a good chance we'll find some in our galaxy someday. Moving on to Hubble. So we now need to think a bit further afield. Hubble was a famous astronomer, and as I said earlier, he was the one credited for identifying that certain blurs or smears through telescopes were not in fact what people thought at the time, which was a close-by nebula or a bunch of gas really, but were in fact a distant galaxy. 100-ish years ago, people viewed the universe as the galaxy. As far as they knew, the entirety of everything was in the Milky Way. Now, the Milky Way is a very, very big place, and to be honest, I can't imagine us ever crossing it. Even hundreds of generations will go by. It's a colossal space. But compared to the space between galaxies, it's tiny still. So Hubble basically told us that the universe is hundreds of billions of times bigger than what we currently, or at the time, thought it was. And this was quite exciting. One of the pieces of evidence he used was this chart here. And this is a plot of distance measured in parsecs. If you want to know what a parsec is, you can read about this, but it's basically a very big distance unit. So 3 times 10 to the 16 meters, or about 3 light years. That's how far light would go in 3 years. That's a unit. And here we have 1 million of them, and 2 million of those units. That's the range at which Hubble's telescopes could view when he was around. And then he applied the Doppler shift method to work out the speed of the things that he was observing, which turned out to be galaxies. Our natural assumption would be if everything's arranged randomly, half of them would be coming towards us, half of them would be travelling away from us. So you'd expect a flat line, and you'd have just as many above it as below it. But that's not the pattern. The pattern is, the further away you look from us, the faster the galaxies appear to move away. So near us, the effect that we're about to describe is minor compared to the random distribution of velocities. So you do still get some that are travelling towards us. But as soon as you leave our local cluster and look further afield, some are moving faster than others, that's the random distribution, but there's this overall shift. Everything's kind of getting pushed out. And Hubble looked at this and he thought about it, and he came to a conclusion. It's not so much that everything's moving, it's the space in between us is growing bigger. And Hubble came up with this equation here. He says the recession speed of a galaxy, that's how fast it's travelling away, depends upon the distance, and it has this factor, this constant, which is now known as the Hubble constant. And this is basically a measure of how much bigger space gets. So how fast does it force things to move for every megaparsec you are away. And you can see it from this graph. If you're 1 megaparsec away, you basically are moving away at 300 kilometers per second, which is a very big speed. Now, Hubble's original data was a bit, well, let's say noisy. It wasn't the most convincing pattern. So people were a bit suspicious. They didn't want to change their entire view of the universe, so people went ahead and they took more data. And one group here did a follow-up just a couple of years after Hubble's main publication in 1929. So before they had data that went up to about 2 megaparsecs. This goes over 10 times further. And now, because we're looking at bigger scales, the uncertainty is less. And for that reason, the data better follows this line. That's a lot more convincing. Hubble won his Nobel Prize for this work. The Hubble telescope was named after him. It took basically every pretty image of space you've ever seen. In more modern times, well, in 2004 this was published, and this little square here represents the data that's here. So that's up to about 30 megaparsecs. If you go now an extra 10, 20 times as far away, using whatever we can find basically, we notice that this pattern follows very, very closely. We're now convinced there is a relationship between how far away something is and how fast it moves away from us. Space must be expanding. Now, if you look in any direction, you see this pattern. There isn't really a direction in space, but let's pretend. If you look to the stars that are towards the north, or the galaxies in the northern part of the sky, you see this pattern. If you look to the south, or the east, or the west, you see the same pattern. It is constant throughout all of space. Like most things in science, our estimates of particular values has changed over time. This graph here shows Hubble's original work and how it was a very, very big number indeed, and people have since refined the estimates. There are many, many, many more surveys that have been done in recent times, and more people have done the analysis, but the interesting pattern is not only are these values now hopefully more accurate because they agree with each other, the range at which they're estimating these values is a lot shorter. I mean, this one here is quite crazy really. It's somewhere between 150 and 600. Can you imagine getting that for maybe your shopping bill or something? It would be somewhere between 150 and 600 pounds. That's a huge range. Whereas these days the ranges are quite narrow. The latest results are published here, and there is still some debate. It kind of depends on which presumptions you build into your working and how you analyze it. But most of these groups are around about the 70-ish region. So the latest one was, more like 67, but between 67 and maybe 76, a range of about 10. Not too bad, given that we can't even touch these things. One of the interesting things that comes from this is you can actually work out the age of the universe from this data. You see, we've said the universe is expanding, and we know how fast it's expanding. That's what Hubble's constant is. It's taking a value of 70 here, 70 kilometers per second for every megaparsec of distance. So we can take this equation and substitute for distance speed times time, and then speed cancels out. Doing a bit of rearranging, we find that the time for everything to get where it currently is equal to 1 divided by the Hubble constant. 1 divided by this number. Now we have to convert from kilometers into meters per second and from megaparsecs into meters. Doing that conversion gives us a Hubble constant of this value here, 2.26 times 10 to the minus 18 per second. 1 over that gives us this rather terrifyingly big number. Converting from seconds into minutes, then to hours, then to days, then to years, turns out the universe is approximately 14 billion years old. Now, based on our studies of how stars form, that also matches up quite nicely. That gives us enough time for 2 to 3 generations of stars to be created, to go through their life cycle, to explode and to scatter. That's quite nice. For reference, current estimates put the planet Earth at about 5 billion years old. So the idea that everything was previously crushed into a tiny little space and then something at some point just went bang, well, it might sound like a rather silly idea. In fact, the name Big Bang comes from a person who was exactly mocking that. He was like, oh, what? It was just like a big bang. And the name kind of stuck. Right? When we look further and further away, we're actually seeing further back in time because it takes quite a long time for light to travel through the universe to reach us. And we do notice patterns. If you look at faraway galaxies, they are not as developed. They don't have as much structure. They are simpler. So we can get an idea that, for at least this zone where there are bright things, up till the sort of first stars, we can actually view what was happening in the distant past. But at about roughly 14 billion years ago, or 14 billion light years away, we don't see anything at all. That's the sort of limit of how far we can look. No matter how good our telescope is, we can't see before then because there hasn't been enough time in the universe for anything that far away to have sent light to us. That kind of reassures us a bit. Before the Big Bang theory was developed, the accepted model of the universe at the time was one that was static. People believed that the stars were eternal, they were always the same, they'd always been there, they always would be there. But this suggests something different, and just by physically looking at the stars you can see some indication of this. The main piece of proof though is what we call the afterglow of the Big Bang, or rather its fingerprint. And it looks something like this. This is known as the cosmic microwave background radiation. The idea was that if the entire universe was at one point all at the same place and had the same energy, then we should be able to somehow see that echo. This would be the lowest temperature of the entire universe. It started off at this rough temperature, which should be the same everywhere, and then over time space has expanded, which has spread out that energy, so it's cooled down, but it should all be the same temperature. Now, we took satellites and we pointed them at every direction in the sky, and each sort of strip of sky produced one little slice on this little mat. So you could imagine making the inside of a globe and then you roll it all out, and this is what you get here. Now there is a texture, a pattern here, but that's actually quite misleading. The result here is that these values are all incredibly consistent. There is only the tiniest of tiniest variation in the background temperature of the night sky, unless of course there's a star in the way. And if you plug in the frequencies of light that we measure, it looks something like this. This blue line is the mathematical model of the temperature we would expect, and the red data is the values measured by the satellite. It's basically a perfect match. The entire universe has the same background temperature, and it corresponds to a particular frequency distribution that our mathematics predict. This was one of the big pieces of evidence that shows the Big Bang Theory correctly describes what happens. There is some debate upon exactly what happened in the different stages, and no one can claim anything at all about the start. And we're not quite even certain about the exact age either. There are some variations, and there could be some parts missing to this story. Like for example here it shows an accelerated expansion. We don't know if that started happening recently or much earlier. One of the other big surprises came out much later. When we extended the range of Hubble's work, first from a tiny dot to a little bit, then a bit further, so far the pattern held, and it became clearer and clearer that he was onto something. But this chart here shows not 200 megapascals, but 10 gigapascals. That's much further than the previous chart. So the previous chart would have been 0.2 gigapascals, this sort of range back here. If you go really far, i.e. you're looking really far back in time, you notice that the data isn't actually a straight line, but rather it's a curve. And different people have modeled different curves based on different data. Our current thinking is that this curve shows us that Hubble's constant, it's constant because it's the same throughout the universe, used to be different. So it changes over time. And the conclusion from that is that the universe is not only expanding and blowing up and getting bigger, it's getting bigger at a faster and faster rate. The rate of expansion is accelerating. And this is quite strange, because we believe that an acceleration would require some energy or something to power it, and we have no idea what that might be. So far, we've went as far as to speculate and say there must be some missing energy in the universe that we don't know about. We can't see it, so we'll call it dark energy. The first stage of any scientific process is blind speculation, and that's currently what we're doing. Lots and lots of people are speculating what that could possibly be and how we might possibly detect it. But so far, it's still a huge mystery. The other big mystery is dark matter. So when we look at a galaxy, it of course rotates, but it rotates in a slightly strange way. We would expect the side that's moving away from us to be redshifted and the side that's moving towards us to be blue shifted. And that is roughly what happens. But if we carefully take images of a galaxy, we can actually color code the entire thing and measure the speed of every single star within it if we look very, very carefully. Now we know quite a bit about gravity, or at least we thought we did. We have Newton's universal law of gravity, and we also know how things spin. That's not part of your higher course, it's part of the advanced higher, but it's very old physics. And putting those two things together, as well as measuring the mass in a galaxy, we'd expect a curve that looks like this white line. That's what we would expect from what we see. But when people take follow-up measurements, when they directly measure the starlight, they can only go so far, and then when they use other measurements, they continue the pattern. But long story short, what we see is not what we expect. The outer edges of the galaxy are traveling far too fast. We don't know what's causing that. One possible explanation is that there could be extra matter in galaxies, matter that doesn't give out light. We call it dark matter. And we have no idea what it could be. None at all. We can roughly measure the amount that we're missing though, assuming it behaves similar to regular matter. And we end up with this chart here at the bottom, which is a real pain because until recently we kind of thought we knew all the physics. We knew the basic picture, the lay of the land, and we were just filling in the details. It turns out every time we think that, we discover new mysteries. And our current estimates look something like this. Of everything we observe in the entire universe, it would seem about 73% of it is dark energy. We have no idea what that is. Another 23% is dark matter. We have no idea what that is. Of the remaining tiny little 4%, almost all of it is stars, and then there's this tiny little fraction of everything else. And of course we're just a tiny little bit of that tiny little everything else. It turns out we really don't know that much about the universe. There's still quite a lot to discover, but that makes it more exciting. The final thing I want to tell you about is something that's particularly nice. Hubble was famous for discovering galaxies exist, but the Hubble telescope more recently made some other discoveries too. It had done loads and loads of work looking at particular stars and nebulas and taken all sorts of photos, but then one day someone planned a new mission called the Hubble Extreme Deep Field, or the Ultra Deep Field. And the idea was they were going to look at a patch of sky that was basically empty, a dark patch. Now the moon here isn't in that position, it's just showing you there roughly for scale. Now if you go outside when there's a full moon and hold out your arm, the moon's roughly the size of your thumbnail. It's a lot smaller than people think. And this little patch, people say, is roughly the size of a grain of sand held at the end of your arm. A teeny little speck of sky. And what they found when they stared at that sky for about 11 days and gathered up all the light was this picture here. Now this picture contains approximately 10,000 little dots, and every single one of them is an entire galaxy. So 10,000 galaxies means 10,000 multiplied by 100 billion stars. All of those solar systems live there. And if you do the math and you assume the whole sky is like this, you end up with hundreds of billions of these galaxies. So the universe seems to consist of 100 or so billion galaxies, each with 100 billion stars, and most stars have planets. Even if life is incredibly rare, the most vanishingly small probability, like winning the lottery 5,000 times in a row, even if it's that rare, there are so many places it could form, it's almost a certainty that it's out there somewhere. That's the nice news. The bad news is the distance is so colossal, chances are we'll never be able to communicate with them. But who knows? There was one final piece of work. The final piece of work was to take this image and analyze the color spectra to work out how redshifted the different galaxies were. And from that, they were able to work out the distance to each one and make that into a 3D model. That's the last thing I'll leave you with. Hope you enjoy it. This is often referred to as the most important picture ever taken by humanity.